Density. Density is a measurement of how compact a material is. Some objects are very dense, others less dense. Water is kind of in the middle with a density of 1. Water's density is 1 gram per milliliter. I brought in some objects here. We're going to test their density. These objects, rocks, if I place them in the water, the rocks sink. And that tells us that they're denser than water. Their density is higher than 1. I also have some metal bolts here, and if I drop those in the water, of course the same thing happens because their density is greater than water. I also have a chunk of plastic. This plastic, if I drop it into the water, floats. That tells us something about the density of plastic. Plastic's density is less than water, less than 1. I also have a piece of foam here that floats in water too because it has a low density. So it's no surprise that these objects behave the way they do. Rock's density is about 3 grams per milliliter, which is more than 1. And iron's density is about 8 grams per milliliter. The density of foam and plastic, foam is about 0.2 and plastic about 0.9, and that explains why they float. Does aluminum sink or float when I put it in the water? Well, aluminum has a density of about 2.7 grams per milliliter. So I'm going to take a piece of aluminum, I'm going to fold it a little bit. I'm going to drop it in the water and we're going to predict what will happen with the aluminum. Since aluminum's density is so much higher than water's, when I place this in the water it should sink. What's going on with my aluminum here? I've got aluminum, a material that is denser than water, and it's floating. You know, even more impressive than this, think about what most large ships are made out of. Most of those ships are made out of iron, which has a density of 8. How in the world are those things floating? So what's the deal with aluminum? Does aluminum sink or float? So I have here a little experiment we're going to try. I have 2 cans of soda. Now these are unopened cans of soda. They're 12 fluid ounces, 355 milliliters. What happens if I test the density of these objects by placing them in water? I'm going to hold these underwater for a minute because I've wrapped them in foil and I want to make sure all those air bubbles that might be trapped get out. And then when I release them, I want you to watch how they behave. You see, there's something different about these 2 cans of soda. This one over here apparently has a density more than 1 because it sinks to the bottom, while this can over here has a density less than 1. So what's going on? Why do one of the cans sink, but the other one floats? They're both made by the same manufacturer. They both have the same volume in them. I didn't tamper with the cans. I'm not messing with you. I didn't poke a hole in one of the cans and let some soda out. These are right off the shelf. One of them sinks and the other floats. What's the explanation? It's sugar. You see, one of these cans of soda has sugar in it. A lot of sugar. The other can has a small amount of artificial sweetener. So if I take both of these cans and dunk them into the water and let them go so we can watch and determine their density, as you may have guessed, the diet soda is the one that's floating, while the regular soda has a density pretty close to 1 or maybe even a little more than 1. So what am I trying to say? What am I trying to show you with this? Obviously there's science to get here, but what's the deeper message? The deeper message is stay away from the soda. It's loaded with sugar. If you're drinking this stuff, you're going to be out swimming in your pool and you're going to sink to the bottom like a rock. Stick with the diet soda. Now we're in the lab and we'd like to find out what is the density of these 2 cans of soda. Doing this is a fairly easy calculation. All you need is the mass, which you can determine using a balance, and the volume, which can be found using this graduated cylinder. So when I place a can of diet soda on the balance, I find out the mass is 372.1 grams. Doing the same with the regular soda gives a mass of 382.7 grams. The next thing I need to measure is the volume. Now you might be asking, why use a graduated cylinder? The volume's written right on the can. It's 355 milliliters. Ah, yes, but that's the volume of the product, not the can. So to determine the volume of the can, I've emptied its contents and completely filled it with water. Then I'm going to transfer that water to a large beaker. The beaker has a scale on it which can be used to read the volume, but that scale is not very precise. A graduated cylinder has more lines on it, so it is more precise. You can see when I'm done, the volume looks pretty close to 355 milliliters. Unfortunately, the graduated cylinder has a capacity of 100 milliliters, so I'll need to fill it a few times to get the total volume. The volume of the liquid measures 89.8 milliliters plus 89.1 milliliters plus 95.4 milliliters and another 97.4 milliliters. Now I have all the measurements I need to find density. I know the mass of the diet soda, and we measured the volume of this can using that graduated cylinder. I can also find the density of the regular soda using its measured mass and volume. We'll assume the volume is the same as the other. So, let's get to it.